Hi universe, I'm AG and let's begin with sequences. A sequence is a special function type that gives a successive expression, usually related to the natural numbers and the zero. A sequence can be finite, infinite, or as the strings a simple group of characters. This is called the n term and is enough to denote the entire sequence. The summations are always defined and must be represented with this Greek letter. Under the sum symbol, we write the start point and the n goes on the top. Now, given these two summations, find the result for each one. Just replace the term with the numbers from the start point to the end and finally sum all. To understand what are indexed sets, let's consider this collection of sets, S and Q. Depending on the function, this unique set can give us output each of these sequences. And here is where we say that this is the indexing set, those are the indexing functions, and these are the indexed sets. An indexing function can involve multiple variables, like this by example. Again, we use the indexing set to get the indexed sequence. Another group of functions are those who implement a practice known as recursion. By example, the factorial of a number is a function that multiplies every number until it reaches the input. This is the factorial of 4 and this is the factorial of 6. By convention, the factorial of 0 is 1. By looking the factorial of 4, we found that this structure right here is the factorial of 3. So we can express the factorial of 4 as the number 4 multiplying the factorial of 3. And this is called recursion. It's like a function referring to itself. In that way, the factorial of 5 can be decomposed like this. This subject will be explained later. For now, we say that every time that a function is referring to itself, the recursion level is increasing. Another example of a recursion function is the Fibonacci sequence that starts with 0 and 1, and the next term is the sum of the last two. For an input like 10, the function will output 55, that is the 10th number in the sequence. But what if we replace this by the last two numbers, f9 and f8? The result is still the same. Decomposing the entire f10 function, we obtain a recursion level of 6. An algorithm must be seen as a series of steps to solve any problem. Usually, we receive an input and after the instructions we set, it will give an output. By example, we want to find the greater common divisor on 258 and 60. What will be the obvious method to solve this? List all the multiples for 258 and 60 and compare each one until you get the greater multiple. Our brain does these comparisons so fast that we don't even care about it. But a computer requires energy and time to solve it. Consider this another method to solve exactly the same problem. Get the module between the terms and continue with the remainder until you get 0. The last divisor is the greater common. This is what we call the complexity of an algorithm, and the last one was by far the most efficient. From the last example, we can extract the complexity definition, and according to the algorithm structure, a machine will take more or less time to solve the same problem. By example, the first method we used needs decompose each number in their multiples and make dozens of comparisons to get the result. In the last method, using the module function, we get the same result in 3 operations. If we add another number to the problem, find the greater common divisor between 3 numbers, obviously we are going to need more operations to give the output. So, according to the input size, we are going to need a way to find the required time. For computer science, we are only interested on find two considerations about an algorithm solving a situation. The worst case scenario, whatever the input is, and the average behavior. By example, we have a set with 9 elements, and we want a function to input the element we want to find and output its position into the set from 0 to 8. The way that anyone do this is by looking into the elements one by one, from left to right, until get the target. In the best case, the target is at the beginning, like the E element. But in the worst case, the target is at the end, that obviously required more time to find it. This operation is known as linear search, and its two words and average cases are given by these expressions. The way as a function behaves according to its input elements is called the rate of growth, and here we have these functions. So let's see how their outputs are increased when the input element increasing. This one is called the identity function. If you input one element, you obtain 1 time unit. If you input 3 elements, you get 3 time unit. For 10, you get 10. The output equals to the input. A logarithmic function is visibly more efficient. When input 4 elements, get 2 time unit. When input 10, only 3.3 time units are required. This looks similar to the last one, but is significantly inefficient. For 5 elements, we get almost 12 time units required. It is said that this is a linear-arithmetic relation. The square function is another inefficient situation when for each input you get the input element numbers by a square time units. Now, in most cases there will be components in your programs that unavoidable will have this behavior. Later we're going to learn how to apply efficient techniques to reduce the time complexity. The important thing to remember here is that a procedure can be measured in terms of efficiency, and to improve it, it must be done by mathematical considerations rather than empirical. In computer science, this rate of growth depending on the input is expressed throughout the big O notation. By example, the linear search we saw before has a O(n) time unit performance. Another technique to search an element in a set is the binary search that has O log n base 2 elements time unit performance, and because its efficiency that we are going to use instead of linear search. That is all for today. Thank you very much for watching our video and stay tuned for the new content.